now we have completed mostly the single degree freedom system and also the numerical analysis part. So now we will start the multi-degree freedom system, and we will try to see that how those what we have studied in the single degree freedom system, how we can able to do the similar type of things for the multi-degree freedom system. So first we will discuss what is the MDOF system, then we will slowly go into how we can able to find out the natural frequencies of a multi-degree freedom system, because here there is a changes compared to the single degree freedom system, that is we are not having a single spring mass system so that we can able to get a particular natural frequency. That is a combination of several spring mass. So what we are getting, that is also dependent on how many nodes we are taking. So it's a little bit different compared to the single degree freedom system, but fundamentally they are quite similar. So we'll study that how we can able to extract the natural frequencies for a multi-degree freedom system, and then that will be mostly the eigenvalue analysis. Then we will move into how we can able to do the dynamic analysis of that using model superposition technique. Then we will also go for the time history analysis, I mean the time domain analysis as well, and we will also study how these concepts will lead to the vibration control for the multi-degree freedom system. Okay, so that will be primarily the scenario. So let's start with the multi-degree freedom system fundamental, that okay, what is multi-degree freedom system. Okay, so if you see that in a single degree freedom system we try to idealize any structure using these three basic component: spring, mass and temper. That are the three fundamental components by which we try to idealize any structure like that. But where we face some problems, so which structures were very much resembles with the single degree freedom system. So if we see that we are having a water tank, like where we can easily see that okay, the masses are lumped at the top portion, so that is very nicely resembled to a single degree. We have a bridge structure like this, so that is like resting on the column, so this gives the mass, and the deck full structure gives the mass, and the columns are giving the stiffness. So that is also quite easily idealized to a single degree freedom system. But if we look like a multi-storage building, let's say, like we have a multi-storage building. So in that case, if we try to see, so in this case, we can see that it is quite difficult to express it as like a single mass, because mass is mostly coming from the floor, because in the floor it is like a quite large area wise, and also it has a thickness, although that thickness is not that much, but the area wise it is quite large. So the main mass accumulation is occurred at the slab level. So now suppose if it is like a several stories, then in each level we have the mass, and also they are connected by some means connected by some columns. So this each column will give some stiffness. So if we try to realize it as like a only single degree freedom system, that will be quite complicated. So what we try to do, we try to realize it as like a, means if we try to draw it, so it will be like a mass. So these are the way the masses are lumping. So whatever the number of story, we will have that many number of masses. So that is like a mass M, maybe M1 first floor, M2 second floor, M3, like this way, so on. And these are the column stiffness. So how many columns are there, we can accumulate it, the total stiffness of that, and we can say that okay, this much is the stiffness coming there. So that is also like a K1, so that is from the bottom stilt portion maybe, then K2, K3, like this way the stiffness are coming. So we can see that the structure is no longer remain only a single degree freedom system. Now this structure has several degree of freedom. We have, instead of a single mass and spring stiffness, now we are having several mass and several stiffness. So here, now if we try to recall how we defined the natural frequency of the structure, we told that natural frequency of the structure was root over of k by m. We had a single k, single m. It can be very nicely defined. We can easily get a particular parameter. But now what happened? Now we are not having a single mass and single stiffness. So which mass you will consider for the natural frequency and which mass you will not consider for the natural frequency? So that's a complicated question, and it cannot be like this way only. We need to see that how these things are happening, because natural frequency is one of the very fundamental characteristics of any structure. So when you have a particular structure, this structure will going to, when suppose if you displace it and if you let it go, it will show some oscillation, and that oscillation will be in some particular frequencies only, and those frequencies are the natural frequencies. So definitely natural frequency will be present in multiple degree freedom system as well, but the point is that we have to identify that how we can get those natural frequencies. Okay, so that is one of the prime aspect what we will going to discuss. Okay, so before we go there, first thing is that we need to write the equation of motion for the multi-degree freedom system. Okay, so let's see how we can able to create a equation of motion of the multi-degree freedom system. So let's assume like we are having a very simple system. I just draw. This is maybe K1, M1, K2, M2, K3, M3. Very simple system. Okay. So how should we think that? So first let's assume this is node 0, this is node 1, this is node 2, this is node 3. Okay. And this one is U0, U1, U2, U3. These are the displacements. Okay. Now suppose if I try to see what happens with the M1 mass, what should be the forces acting on the M1 mass. So if you think that if we are displacing M1 mass in U1 amount, okay, then this spring will give the force Q1 into U1 minus U0. Okay, this spring will give a force Q1 into K2 into U1 minus U2 amount, and this mass will have its inertia M1 into U1 double dot. So we can see that three forces will act in the negative direction. So we can write M1 U1 double dot plus K1 U1 minus U0 plus K2 into U1 minus U2, that will be equal to 0. First case, if we are thinking that there is no forces acting on the structure, it's like a free vibration case, then we can say that should be equal to 0. Or if we are saying that okay, there is some forces F1 is acting on that, so then it will become F1. Simple. Okay, any doubt? No. In the second case also, we can easily able to write M2 U2 double dot plus K2 into U2 minus U1 plus K3 into U2 minus U3 equal to F2, and M3 U3 will be equal to K3 U3 minus U2 equal to F3. Okay. So if I try to write that in the matrix form, how can I able to get that? m1, m2, m3, u1 double dot, u2 double dot, u3 double dot. Another important thing we need to notice that u0 is actually 0. It is fixed. So we can remove that u0 here and we can put it 0. So what we left with? And here we will have u1, u2, u3. So first thing is k1 plus k2. Second term will be minus k2, minus k2, k2 plus k3, minus k3, minus k3, k3. So that will be my full equation of motion. So the first term, what we get here is, you can see that has the acceleration terms, that is u double dot. So different u component like u1, u2, u3, u4, and their double derivative with respect to time that are placed here. Then these are the displacement terms, okay, and these are the forcing terms. Then these acceleration terms is get multiplied with the mass matrix, okay, and these displacement terms is get multiplied with the stiffness. Very similar manner, if you recall, m u double dot plus k u equal to force. Same manner, instead of here m is not a single number, rather it's become a matrix. U double dot is not again a single number, it's become a vector. K is not a single number, it also become a matrix, and U becomes a vector, and F also becomes a vector. Okay, so that way we can able to understand that point. Now, interesting thing is that, okay, so now we can see primarily the mass matrix is diagonal here, okay, because we have already lumped the masses. So wherever the mass is, if you displace it, it will give the inertia. That inertia effect is not coming on the other masses directly. I mean, that can come to the stiffness, but that is not coming through the mass, through the inertia term. Okay, got that point? So this way, the mass matrix is singular. Means if you give a force on a particular mass, that mass only will accelerate, not other mass. Okay. Yes. So this way we can able to get that. Now, one important point is that making so we can see that making the mass matrix is not difficult, because wherever we are having the masses, there we need to assign some degree of freedom. So like for example, we have a mass m1 here, we will assign it u1. Simple. We have a mass m2, we assign this u2. We have a mass m3, we assign u3. So wherever we have mass, we are giving a degree of freedom. So mass into degree of freedom, that portion is clear, and whatever is the mass, corresponding degree of freedom, we will put that corresponding masses. So that point is very easily we can able to make mass matrix and stiffness. But stiffness matrix is not that easy to make. Means yes, you can write all the equations like this way and you can able to get it, but you can understand. Suppose let's say if you try to analyze something 50-story building. Okay, because come on, we need to use for this type of analysis, and that's why we are studying this type of courses. Otherwise, like for 1 or 2 degree of freedom, yeah, nobody started those things. So yeah, so if you see that once we are making this like so many equations, then writing that many equations itself will become a big challenge. Like 50-story building means 50 degree of freedoms. Now you have to write 50 equations of motions. Automatically the method is getting complicated. So obviously there should be some better way to write that equation of motion by which you can just like do it almost like in blink of eyes. So how we can do that? So you can see that stiffness, so like first let's see, stiffness is like this. So it is connecting the two degree of freedoms. Okay, so let's say this is I, this is J, this means U I U J, and this is something like K. So then stiffness is coming somewhat like this, K minus K minus K K with UI UJ equal to Fi Fg. So that is like a basic stiffness is acting like that. Now what we have to do? We have to identify where the stiffnesses are and that particular stiffness connects which two degree of freedoms. Make sense? For example, if you see K1, okay, once we are making K1, okay, maybe I will come to K1 last, at last. Start with K2. So K2, if we see, K2 is connecting which two degree of freedom? U1 and U2. Okay, so now we can see here U1, U2. Here also you can write U1, U2. Here you can see this is very nicely UI, UJ, UI, UJ. So it is just connected. So you can see here U1, U2, U1, U2 minus K2, K2 minus K2 minus K2, K2. So you are having this matrix. Agreed? Anybody? Any doubt? No doubt? Very good. Now see K3. K3 is connecting U2, U3. U2, U3, U2, U3. You see? Makes sense? You are just placing that. And wherever you have interaction, you just add that. Any doubt? Anybody? Okay. Perfect. Clear? Very good. Now the question becomes, what happened with the K1? Because K1, if you see, just only K1 is there, not any other thing. So that is, so that's why you see I wrote that U0 here at beginning. So it is somewhat like this U0. So it was somewhat U0, U1. So you will have K1 minus K1 minus K1 and K1. Okay. So then that matrix is not 3 by 3, rather it's become 4 by 4. Okay. And you will have one row additional. Just let me rewrite it. If I go like that way, then what will I do? I will write it here U0, U1, U2, U3. U0, U1, U2, U3. Top portion is like not required to write at all. This is just to show that okay, you can thought it. So just put it very simply, K1 minus K1 minus K1, K1. Then K2 minus K2 minus K2, K2. K3 minus K3 minus K3, K3. Done? Simple. Now what happened? Now your U0 is 0. Forget that. U0 is 0. Just you can forget that. So you left with this part only. And that part is this. You see? Makes sense? Any doubt? Any doubt? Any doubt? Anybody? Yes. So there is also another point I would like to mention, that is, if you see if you are not removing that u0, means suppose if we just use that full matrix like k1 minus k1 minus k1, k1 plus k2 minus k2, k minus k2, k2 plus k3 minus k3 minus k3, k3. If we just use that full matrix as it is, then we will see that determinant of that matrix will become 0 because it's a singular matrix. How it can be a singular matrix? Okay, proving that is much difficult. Let's try with this one, that small one, k minus k, k. How to calculate the determinant? A, B, C, D. If it is that A, B, C, D, the determinant is AD minus BC. So here k minus k minus k, k. Determinant will be k square minus of minus k square. Then means k square minus k square, that will be 0. So we can see that stiffness of each submatrices are 0. Means the determinant of each submatrices are 0. So therefore, if we are adding them or making the matrix with those submatrices, that will be also 0. So you must have at least one non-singular. Otherwise, what will be the problem? If your stiffness matrix is singular, the problem is that you cannot able to invert it. For example, if we just forget the mass, if we just forget the mass for time being, means if you just forget the mass for time being, so my equation is something like that. Okay, if I just forget the mass, then it is ku equal to f. How you can calculate u? K inverse of f. Simple. Now if your k matrix is singular, can we able to get k inverse? No. Simple. So we cannot able to find out what is the reductive. Now you can you able to correlate, because that we got it from the mathematics, but we are solving a physics problem. Is it really true for the physics, or if we can able to cross check whether it is correct or not, for what it is justification? So let's see. We had our system. I am now putting u0 not 0, u1, u3, u4, k1, k2, k3. Okay, now let's say you apply some force here, f0, f1, f2, f3, or maybe you are feeling maybe uncomfortable that okay, I should not apply any force on f0, means u0, because previously it was not there. So forget it, leave it. Okay, still if you try to solve it, try to think physically. You have like some masses, tuck tuck tuck, 4 mass, they are connected by 3 springs. Now you apply the forces on that. What will happen? Exactly, it will become like a rigid body. All will move like a train. So you cannot able to get any solution. Got that point? Because there is nothing which is holding it. Apply the force on like a body which is completely free, it will go. Simple, done. Any doubt? So that actually shows you will not get any value of u. And also if you see that in this case the stiffness is almost like 0, that means your displacement is infinite. If you do it like f by k, and k is 0, then f by k is equal to your u, and u is become infinite. That means you are applying the force and it will go. Simple. Go. Where it will go, you don't know, because we are not considered at all the velocity and all other things. It is the instantaneous process. Apply the force, it goes. Done. And actually if you see, yeah, so that gives the infinite thing. Okay, so we will get this way. So is that clear? The concept is clear from the physics aspect, from the mathematics aspect. Okay, very good. Now once you are making this fixed, then what will happen? Then you hold it, and now they cannot able to go. And now that also reflect in your mathematics that your stiffness matrix is now no longer singular. It's become a non-singular stiffness matrix. Therefore, you can able to invert that matrix and you may get the solution. Does that make sense? And now you will get the definite values of u1, u2, u3, all those. Okay. Clear? Any doubt? Any doubt? At any point? No doubt. Very good. Because these things are so important, because these are the fundamentals we are talking. Like if there is anything doubt remained, it may create some problem. You have seen how these things get exponentially increased. Already in the single degree freedom, you have an idea. So here also it will be happen like this way. Don't worry. So if you have any confusion, please make it clear. Okay. And this is multi-degree, much more complicated, because they are single degree. You have seen that making the natural frequency is very easy. Here, making natural frequency itself is complicated. So you can understand the story will be not at all simple. Okay, no issue, but don't get afraid. Yeah, so we got that point, and we are making now our matrix simple, and we have also seen how in a very simple manner how we can able to write a stiffness matrix. Okay, maybe I will give one example type thing, like a lot of people are telling that do some example. Okay, let's do one small example. Like for example, this is the system. Now let's say if I connect another spring like this, maybe I wrote it K4. Can you write the stiffness matrix? Yes. How? Please, anybody, please tell me. Because writing the mass matrix is not a big deal. That will be even same, because mass matrix you are just having u2 is missed. That okay. Maybe I'll just put it u1, u2, u3. Okay. So tell me. First we will put k1 minus k1 minus k1 k1. Then k2 minus k2. K4. How to put? Yes, please. Where? Matrix is like you can tell 1 by 1, 1 by 2. So that way, please tell where I should.
At 2 by 2 will have your statement.
Perfect. Then at 3 by 3. 3 by 3 here or here. 3 comma 2. 3 comma 3 here. Here. That is 4 comma 4. Come on. Come on. 1, 2, 3, 4. This K3. Not K3. That will be K4. K4. Minus K4 minus K4. Very simple. Think. They are connecting 1 and 3. Here 1, here 3. Just you connect 1, 3, 1, 3. Done. Nothing. This is very simple thing. Okay? But it's better I solve it one time. Then in exam it will not be that difficult. Okay? Good? Nice. So this way we can write the stiffness matrix. But if you see in the mass matrix, it is just remains simple diagonal. Like you will here, and then this is 0, so you will cut it, and we will have the mass matrix like this: m1, m2, m3, u1, u2, u3 with double dot. Plus this, that is equal to whatever. Makes sense? Clear? Clear? Everybody? Any doubt? Good. So we got the stiffness matrix. How to do it? Okay. Nice. Now the important thing is coming into picture. But once we get the mass matrix, we got the stiffness matrix. Now the things is natural frequency. Now that we have to think now. Good. Okay. So now let's come into the point. What do you mean by natural frequency? If we excite a structure at that frequency, the structure will be in the resonance. Agreed? If I give the definition like this one, agreed? So now, if we are having 3 degrees of freedom or maybe 2 degrees of freedom, then the structure will have 2 frequency points where it will start like a vibrating vigorously. At those 2 particular frequencies, the structure will vibrate vigorously. So these 2 will be its natural frequency. Okay. And in the natural frequency, or if I tell it in the mathematically, natural frequency or the eigen frequencies are a plane from where the stiffness matrix get decoupled or the stiffness matrix become diagonal. Yes, I know that's obviously it is getting really complicated. So forget the 3 degree of freedom first. Let's go to 2 degree of freedom because we can able to draw it. 3 degree of freedom drawing will be difficult. Then we can thought it for the multi-degree freedom. Okay. So let's take a 2 degree freedom system. Like for example, let's just think we have a 2 degree freedom. M1, M2, Q1, Q2. Okay. Equation of motion M1, M2, U1 double dot, U2 double dot plus K1 plus K2 minus K2 minus K2, K2, U1, U2. Okay. Means multi-degree freedom is also so simple, you can write the equation of motion like this. You don't need to think at all. If you just follow this technique properly, you will be literally expert to write the equation of motion. Not at all any problem. You will not make any mistakes on that also. Okay. Yes, then the point is where what was the point? Yeah. So if you try to see that, if we try to solve this equation of motion, just think that they are zero, like nothing is applying on that. Like we are trying to first calculate the natural frequency, and natural frequency we calculated for free vibration, not force vibration. So free vibration means F1, F2 all become zero. So here if we try to think, then how we can able to solve that? Our target is to calculate a ratio between U1 and U2, because we cannot get any particular value of U1 and any particular value of U2. Because try to remember, in case of single degree freedom system, once we were doing the free vibration, how we get the solutions? We are never get any displacement. We are giving some initial displacement, and accordingly we try to see how the solutions are coming. Okay, because free vibration there will be no deformation, because we do not have any force. Whatever we have given the deformation, it will come like that. We have also seen the phase portrait that okay, how much energy is there, and from there it is happening. So energy means much more complicated thing happens, because that may have velocity, that may have displacement. But if we just talk it only from the displacement point of view, that is like one axis of that phase portrait, that okay, we are starting from any point and it goes. Okay, so we are assigning some values. Here also, if we think in the very similar manner, we have to assign then 2 points, U1 and U2, not only a single point, because we are now having a 2 degree of freedom system. So initial condition will be for the 2 points. So previously initial condition was 2 number, one is displacement, another is velocity for a single node. here it is 4 for 2-point displacement and velocities. Agreed? All of you? Any doubt? Just we go increasing with the number. The previous thing, previous all ideas are remain same. Just we are, instead of having a single degree, we are now having 2 degrees, so it is 2 times more. Okay. So now, if you think in the last case, how do we solve it? We try to solve that. Okay, the first portion is giving something equal to 0. That is the characteristics thing we try to make. Means if I just try to do it recalling again, so you can see that we had a mu double dot plus ku equal to 0, and our target is to calculate the natural frequency. So we try to find some portion before u which will become 0. So we do what? We assume u equal to e to the power of lambda t. We substitute that. So we got it, lambda square e to the power lambda t plus k into e to the power lambda t, that is equal to 0. So we say, so m omega square m lambda square plus k, that is equal to 0. And from here we got lambda square equal to minus k by m, and we got it that lambda equal to I times root over of k by m, and we just say that omega equal to I times lambda, and that is become, so that gives omega equal to root over of k by m. Makes sense? That we did in the single degree freedom case. So we, where is that point? Is that we need something like this, that is the characteristics. Now here, how the characteristics will come? We can try in a very simple manner as we did in the last case. We can assume u1 equal to maybe u1 into e to the power of lambda t, and u2 equal to u2 into e to the power of lambda t. Okay, good. So if we start substituting it, okay, if I take it m1 lambda square m2 lambda square plus, or let me just write it in a compact one, m1 lambda square plus k1 plus k2 minus k2 minus k2 m2 lambda square plus k2 with u1 e to the power of lambda t, u2 e to the power of lambda t, that will be equal to 0 0. Okay, now if your solution is a non-trivial solution, then this cannot be 0, because if this becomes 0, that means either u1 0 or u2 0, or means u1 u2 both 0, or your e to the power lambda t becomes 0. E to the power lambda t cannot be 0. Okay, and u1 u2, if they become 0, the amplitude, then you are just solving for 0. That also makes no sense. So you can say that these becomes your characteristics. Okay, m lambda square plus k1 plus k2 minus k2 into m2 lambda square plus k2, that becomes your characteristics equation. Very simple. you can think that mass matrix multiplied by lambda square plus stiffness matrix. Very simple, absolutely similar to the single degree of freedom. Mass multiplied by lambda square plus stiffness. Any doubt? Mass multiplied by lambda square into stiffness. Previously we did like that. Here instead of mass it become mass matrix. Mass matrix multiplied by lambda square plus stiffness matrix, that becomes 0. Agreed, all of you? Anywhere, any doubt, anything? Because if we have doubt here, it's better to clear it up. Already exponential terms are coming into picture, so don't get it that far. Okay, perfect. So now if we think that, yes, so now you are having m1 lambda square plus k1 plus k2 minus k2 minus k2 m2 lambda square plus k2, that determinant need to be 0. That was my solution. Exactly, that was the meaning of that characteristics equation. Okay, fine. All of you agree? Good. So if you think, now try to solve it. Very simple, not a big deal. Nothing to think that much. It can be solved. m2 lambda square plus k2 minus k2 square, that is equal to 0. Okay, so m1 m2 lambda to the power 4 plus k1 plus k2 m2 plus k2 m1 into lambda square plus k1 plus k2 into k2 minus k2 square, that is equal to 0. Just expand it, nothing else. Multiply all the terms with patience. So I can say that a lambda to the power 4 plus b lambda square plus c, that is equal to 0. Okay, very simple. Whatever the term is coming, hardly matter. This can be written as a lambda to the power 4 plus b lambda square plus c, that is equal to 0. What will be the solution for that? Lambda square will be how much? Minus b plus minus root over of b square minus 4ac by 2a. So we will get the lambda square. Agreed? Good. So we get lambda square. Now what? So once we get lambda square, then lambda will be plus minus of that, simple, plus minus of this root of that. Yeah, so lambda will be plus minus root over of minus b plus minus root over of b square minus 4ac by 2a full root. Okay, so this gives how many values? 4 values exactly. Lambda 1, lambda 2, lambda 3, lambda 4. Previously we used to had how many values? 2 values. Now we are getting 4 values. Make sense or not make sense? Okay, very good. If it makes sense, then try to see what we get. Then what we had assumed, that was our assumption. u1 equal to capital U1 into e to the power lambda t and capital U2 into e to the power of lambda t. Let's see. So your u1 will become capital U1. So now we have to write it with the different name because so many lambdas will be putting there. So maybe like we can say u11 e to the power of lambda 1t, u12 e to the power of lambda 2t, u13 e to the power of lambda t3 plus u14 e to the power of lambda 40. Automatic, we will have that many number of lambda, so roots will be that many. Previously also the same thing used to happen. We will have e to the power of lambda 1 means something like a1 into e to the power lambda 1t plus a2 into e to the power lambda 2t. Here also the similar thing will happen. And u2 will be equal to, maybe we can say u21 e to the power of lambda 1t, u22 e to the power of lambda 2t, u23 e to the power of lambda 3t, u24 e to the power of lambda 4t. Get that? All the values of lambda are here. Okay, 4 values of lambda we got, and we will get the 4 expressions. Good. But yes, okay, we got that. But what we get from here? So what do we get from here? Anybody? What was the target? Not, I mean, there are 2 targets actually. First thing is to find the characteristics equation, like previously we had m lambda square plus k, that we try to first find it out. That we got. Good. The next thing is, yeah, so that lambda square will give us the natural frequencies actually. And then the second thing is that to try to see what happening with the u1 and 2. Okay, so we got some expressions of u1 and u2, that how they are changing with the time. Okay, so now let's focus on the lambda, that what is lambda actually. So in previous case we have seen that lambda is actually become I times root over of k by n. Okay, so therefore we decided that, okay, sometime instead of lambda we can put I omega. We did it in the single degree freedom case once we were doing that, because e to the power I omega, then omega will be a real number, not a complex or imaginary number. So we can able to think that problem in that way. So here, if we try to little bit do that in little bit more terms, then what can we found? We can see that m1 m2 lambda to the power 4 plus q1 plus k2 into m2 plus k2 m1 plus q1 k2, that should be equal to 0. So your C is k1 plus k2 and your m means your A is m1 plus m2, and this term is like a little bit bigger term. B term is little bit bigger, and in that equation unfortunately B is more dominating term. B is like B square and all those things has to be done. So nothing to do. Yeah, so primarily like, and also there is no meaning of solving that as well, because it may change for different configuration. If you put, your equation may come differently. Okay, so we can do accordingly like that, no problem. But whatever the values of lambda we got, yes, so that value of lambda will tell that these are the natural frequencies. Okay, and from there we can also get some specific type of u1 and u2, because they also cannot be anything random. So that way we will getting that one. So now we had this equation and we saw that solution is coming like that. So equation was this one. Now if I try to substitute these lambda square here, what can I get? So if I see that this equation was actually m1 lambda square plus k1 k2 minus k2 minus k2 m2 lambda square plus k2. Now if I try to put that value of lambda and try to see that, then what will happen? This matrix will become 0 by 0. Make sense? Okay. This matrix will become 0 by 0, means all the term will become 0. No, it will not become 0 by 0. When it is not become 0, 0, 0, 0. No, it will not become like that, because minus k2 cannot become 0. That is for sure. They do not have anything lambda, and other terms will also not become 0. Its determinant will become 0. Instead of matrix, if we try to solve it by like a hand calculation, how would you like to solve that? It's a 2 by 2 matrix, so it's not a problem. I'm not asking to solve like a 10 by 10 matrix or something. Even 3 by 3 will become very difficult to solve it like normal. Yes, so how to do that? Our target, okay, first let's discuss what is our target. Our target is to calculate u1 and u2. Okay, we are not going to invert it, because if you do the invert, it will automatically go there and it will become 0, because there is some 0 by 0 thing, 0 0, and we know that this matrix itself is 0, and this matrix itself is 0 matrix. So we are multiplying like 0 with some number equal to 0. So definitely we cannot say that we will invert the 0 and we will solve it, so it will become undefined. That we cannot do. Okay, but what we try to do, we will try to diagonalize this full thing so that we can able to get a correlation between u1 and u2. What is the relationship between u1 and u2? Okay, so for that we can try to write this matrix into a upper triangular matrix or a bottom triangular matrix. That is the Cholesky's decomposition. Let's try to do that. Again, the linear algebra. Okay, so let's try to see how we can able to do that. Okay, think it like a, just like if we, as I say, that will be very simple. We do not need to think that big things. Simple. We have the first equation, that is m1 lambda square plus k1 plus k2 into u1 minus k2 into u2, that is equal to 0. Okay, simple. And second equation is minus k2 u1 plus m2 lambda square plus k2 into u2, that is equal to 0. So if somebody asking you that, okay, tell me, if I put u2 equal to 1, what should be the value of u1? How we can do that? We have two equations. Just take either of the equation, not a problem. So if I just choose the last equation, I can say u1 equal to m2 lambda square plus k2 with a minus sign. The minus sign is already there, divided by k2 should be my u1. Very simple. I just take it to the right hand side and just divide by q2. Simple. Nothing. It's absolutely all right. Okay. And I'm not doing any linear algebra or anything. Just like a normal algebra. It's just go there and we get that. Okay. So what will be? So that gives an expression that u1 and u2 are related like this way. So whatever the value of u2 you put, your u1 will be m2 lambda times m2 lambda square plus k2 divided by k2, or we can say m2 by k2 into lambda square plus 1 times u2. Okay, okay, any doubt? No doubt. Now you see lambda square has how many value?
2.
Lambda square has 2 value. Lambda square has 2 value. Lambda has 4 value, but lambda square has 2 value. So these relationship give me 2 values of u1 for a particular value of u2. Make sense? Getting the point? Any doubt? Any doubt? We are having lambda square 2 value. If I substitute here, the 2 value of u1 I will get for a particular value of u2. So if I just think that u2 equal to 1, I will have 2 value of u1. Okay, good. Now actually this so we can say that from here. So in this problem, whatever the thing we got, for u2 equal to 1, we will have 2 value of u1. Okay, and that we just used only the second equation. So if I use the first equation also, u1 I am just substituting this one, u2. So you see that again I will go back to this equation. If you just think that I am multiplying with the k2 here and k2 square, I am just going back to the first equation. So this is another way how you can proceed to solve the problem. And instead of directly calculating the eigenvalues like this way, you can also able to do it like you are trying to first solve the one equation, get the value how u1 can be written as u2, then substitute u1 in terms of u2 and try to solve what is the value of u2. So that is nothing but the method of substitution. Means either you can go directly by the like it calculating the determinant, or you may able to go by method of substitution that you are calculating one after another. Okay, can do that. Very good. And this actually shows little bit more clearer manner that how u1 and u2 are correlated. So once you are putting the lambda square value, the first value, then you will get one type of relationship u1 equal to u2, like some particular relation, and then another case if you put the second value of lambda square, you will get another set of equation that u1 and u2. Now the u1 u2. Okay, and this thing if you see mathematically, these are known as eigenvectors. Okay, that true value of lambda square is the eigenvalues, and these two relationship of u1 u2 are the eigenvectors. Because what are happening, you are having u1, maybe I am just putting u1 1, that is to represent that coming from the first lambda 1 square, and with u2, and another case you are getting the solution u1 2 with u2. So these are the two possible cases you are getting, and this is for lambda 1 square and this is for lambda 2 square, where lambda 1 and where lambda square has two values. So once you consider the first one, you are getting u1 1 with u2, and second case you are getting u2 1 2 with u2. Makes sense? So these two are mathematically known as eigenvalues, and these two are mathematically known as eigenvectors. Okay, now the question may come, why they are vectored? We can just say that okay, they are having the like a column type thing, that's why they are vector, but that also has its meaning that okay, why it is exactly happening like that. Okay, so up to this stage, is it clear? As we have not introduced any mathematics still. It is just like a very normally we are solving it, like writing the equations, substituting this, we are solving it. I think that up to this stage there should not be any doubt. But we get something little bit strange thing that u1 has two relationship with u2. That if we are having some value of u2, u1 can be two different values, and they are corresponding to two states of the system, because lambda 1 and lambda 2 are the states of the, means they are the eigenstate of the system, so they are dependent on that some sort of way. That's some concept we found in a very simple manner. Okay, any doubt up to this stage? Now let's see or maybe if I just forget the force, that will be equal to 0. So this full thing can be done in a very nice manner. In the MATLAB, we have a command EIG. If I write EIG command and then K comma M, then this will give me the two things, eigval and eigvec. Means eigenvalue and eigenvector can directly be obtained by supplying these two matrices. Okay, to supply these two matrices, whatever the K matrix, whatever the M matrix, it will automatically give me what is the eigenvalues of that. Okay, good. So now whatever we are getting the eigenvector, if I just say that is the phi 1, phi 1 will basically containing u1, u2, like this way, that whatever the terms are there, you will get it there. Okay, and that will be also like a matrix form, it will be coming. So if you just use this comment, and suppose you are doing for the n number of system, n cross n system, then you will get a eigen vectors like this way. Okay, so this is for the corresponding to the first mode, second mode, third mode, fourth mode, fifth mode, like this. Oh yeah, so like if you see also in that case, this is, if you say this is my first mode, this is your second mode, third mode, like this way, and for each case you are seeing that your eigenvectors are not same, your eigenvectors are different. Okay, so here you will also get that eigenvectors corresponding to different eigenvalues, because that eigenvalue matrix will be a diagonal matrix, and that corresponding values you will get that vector. Okay, that will happen. So if I just call them as a phi 1, phi 2, phi 3, phi 4, like this way, phi n, and here you will get omega 1, omega 2, omega 3, omega 4, like this way, or maybe lambda 1, lambda 2, lambda 3, like this way you are getting. So you will get that. Okay, now the interesting thing is that we have a matrix u double dot plus k matrix u, that is equal to 0. Okay, now if I pre-multiply with something phi r maybe, so that is phi r transpose.
So here if you see, this is n cross n. So if I just take one column, that will be n cross 1. That transpose, that means 1 cross n. Okay, m is how much? N cross n. And u transpose, that is how much? That is also n cross 1 plus again phi r transpose k u n cross 1. So this one will become a single number, 1 cross 1. This 0 is like 1 cross 1. This is n cross 1. Okay. And u, how u can be changed? U will be changed as phi r times. Yes, so here what I am doing, I am actually changing the coordinate system. We have, first we were using the u1 u2. Okay, now from u1 u2 I am trying to going to some coordinate system where with the aim that my stiffness matrix and mass matrix, already mass matrix is diagonal and stiffness matrix will also become diagonal. Then what will happen? I will just have like a single equations, no complicated stuffs. Perfect. Because if you see you are solving, if you see you are solving now a system which is this with terms plus this is full populated with something, then problem is where this into this plus now all the things will come. So you cannot able to solve it directly, like you have u1 double dot plus u1 into plus u2 plus u3 plus u4 u5, all those things are started coming into picture. So you cannot directly able to write it. But think, in the single degree freedom system our life was very simple, that we have m u double dot plus k into u, that is equal to something. So we are just assuming that u equal to, let's assume e to the power of I omega t or I omega t, and or maybe u1 e to the power I omega t plus v2 e to the power I omega 2t, whatever, and you substitute it and you get the solution. It was so simple, but now it is no longer that simple, but we are deserving for that type of way, that if we can able to go there, again our life will be simple. Okay, so with that vision we are changing the coordinate from u to some q with a hope that we may able to make our stiffness matrix diagonal. Make sense? So diagonal stiffness matrix will help in that thing. Good. Now this changing of coordinate is very similar to one problem what we all know very much. I believe you know that very well. That is the Mott circle. Although that is a complete solid mechanics thing, but why I tell that, because that is they have a resemblance. There we try to find out the principal stresses, and we try to shift the coordinate system in such a manner, we try to rotate or shift the coordinate system in such a manner that all of the stress tensor will become diagonalized. Okay, so we had some normal stress, some shear stress, but once we rotate the coordinate system, we will be in such a coordinate system where we are only having the principal stresses. Shear stress will become 0. Make sense? Here also we are trying to do the same thing, so that our system will be reoriented in such a manner that we will not have any non-diagonal terms. Make sense? Is that clear to all of you? with the we already mass matrix is diagonal. Mass matrix is not non-diagonal. Mass matrix is diagonal. So we try to change it in such a way that our stiffness matrix will become diagonal, and our life would be some sort of easy. Okay, good. So with that hope, we do this. Okay, so obviously we do something with some hope only. So we do that thing with this hope that U equal to phi r into q. Okay, maybe you can say this is QR also. QR, I think, yeah. That Q can also be changed. QR. Phi r times QR. Okay, so now if you think that way, so just try to understand that whether dimensionality is correct or not. So U is n cross 1, phi r is n cross 1, because that is one of the term of this thing, one of the column of that full thing, and QR is 1 cross 1. It's a single point I am trying to mapping it. Okay, good. So now if I see, so if I just substitute it here, phi r transpose m QR plus phi r transpose k phi r QR, that is equal to 0. Yes, QR double dot. Absolutely, QR double dot. Agreed. What is the dimension of this equation? 1 cross 1. Perfect. So this is just a normal equation, simple. Can I say that this equation is a single degree freedom system equation? Can I say that? So I think now we hope that we did that. Yes, but there is some problem still remained. So this, at least we can see this become like a single degree equation. But we made a cheating here. Where is the cheating? Tell me, where is that cheating? Or can we really do that? Or somewhere we made something what is not allowed actually to do. Huh? QR double dot is fine. No, obviously means Q, and that is with the time derivative, QR double dot. That is okay. That is okay. But life cannot be that simple also. Like we just did it and we get the single degree equation. That's something weird. Yeah, student matrix get changed. You see? Now this is a student matrix. Hello. And that become like a, you have a n cross n matrix, now you have a 1 number. That's the problem. See, where is the problem? In that assumption. Here, if I see n cross 1 system, I try to only project into a single point or like a single axis. Like if you see it is a n cross n axis, then I try to just map it to a single axis. That is okay. I take the projection. How you go opposite? That you cannot go. Because you have just a single point, and now how you can able to get that original image? You cannot able to get. You can only able to project a n cross n system into another n cross n system, not a reduced order. So what you have to do? The mistake is this should be the capital phi, which is that full matrix, which is n cross n, and you can substitute it to Q again n cross 1. That is fine. That is allowed. There is no problem. Then what will happen? Then q n cross 1 should be equal to phi inverse u n cross 1. Means you have to make your other thing also, na, because then what will happen? You may get the q value, fine, but that q is of no use. What will you do with that q? Means in the previous case, that qr, if you think, you cannot use that qr because you don't know how to go back from qr to u. There is no single direct correlation. Because that matrix you cannot able to invert, because that is the n cross 1 matrix. N cross 1 matrix you cannot able to invert. So that point was not there. Got that point? Where was the problem? But still, don't worry. Still we have somewhere in the question. So we cannot write in that so simple manner. But so this is somewhat not the directly we can do. What we can do? We can do phi transpose instead of phi r transpose. Phi transpose m phi q double dot plus phi transpose k phi q, that should be equal to 0. And this matrix is, so this sets of equation is n set of equation. So that is n cross 1, like last term will be n cross 1. Okay, because now you can, if you see, this is n cross n, this is also n cross n, this is again n cross n, this is n cross 1. So full thing become n cross 1. Okay, so phi transpose m phi, that is into q, that one is coming, that then phi transpose k phi into q, that is equal to 0. Now the thing is that if we can make this k diagonal without hampering the diagonal thing of this, we are done. Make sense? Okay, is that all right? Our target, if you can recall, that is to make the K matrix diagonal. Okay, we came somewhere here where we have changed our coordinate system. We multiplied with the eigenvectors and we are more or less somewhere here. Perfect. Now our target is to make the things diagonal. Perfect. Now here we have to use the one important property of the eigenvectors, because we did not use the phi matrix randomly. This phi matrix is the eigenvectors of the system. So whatever the system is, that has its definite eigenvectors. It is not that you are randomly putting any matrices there. They are the eigenvectors of it. And we all know the eigenvectors are orthogonal with each other. We have discussed orthogonality in the Fourier transform as well. What does it mean, orthogonal? Yes?
Phi 1, phi 1, 1, or phi 1, phi 2.
Yes. First thing is not that correct, but the second thing is correct. Phi 1 into phi 2 will be 0. Exactly. Because that is the orthonormality. You don't know that whether they are orthonormal or not. If they are not orthonormal, then first thing will not be valid. That may give some value. But that is 1 only will happen if they are orthonormal. But if they are not orthonormal, you cannot assure that they will be 1. They maybe have some value. Okay. So, but they are orthogonal for sure. Orthonormality we have to enforce after that. So that we will also do, like we will make the eigenvalues orthonormal as well. But that is the second step. First we assume they are orthogonal. We will also show how they are orthogonal, what is their representation in the space, so that we can easily see that eigenvectors they are orthogonal with each other. Okay, so let's see. So once they are orthogonal, then we can say that phi R transpose with k into phi maybe j, that should be equal to, so this is n cross 1, this is n cross n, this is n cross, sorry, this is 1 cross n, this has a transpose, this is n cross 1, so this will be like a 1 value, that will be 0. You got that? Means if I take, like let's say I take this one and I try to multiply with this one, not like this way, one is inverse, so what happen, I mean sorry, transpose, so I just take it, it become like this with the stiffness matrix full and multiplying with this, so phi 1 stiffness transpose with stiffness matrix into phi 3, just for example, it should become 0. Then what will happen, because if I just try to little bit express it in the form of the column space, so if you see that, do you know, do you remember the column space? Then you should refer the video of Gilbert-Strang linear algebra. That's a very nice video. You should see that. So there you can able to understood that thing. Although I'll try to explain that. So we are basically having this way that matrices: phi transpose matrix, K matrix, and phi matrix. Okay. So what is? So this is my phi 1, phi 2, phi 3, phi 4 like this. So these are transpose matrix, and these are my phi 1, phi 2, phi 3, phi 4. Okay, and this is full my populated matrix. I'm just assuming it is populated because it may be populated. Like if you have like a several spring connection here, there, it will be populated matrix. Okay, so suppose if I try to see, if I try to see the multiplication, how it happens. This is multiplied with this and situated at that particular point. Then this is again multiplied with this and situated here. And suppose if I just go, if I just try to do these two things, then what will happen? Like this is phi 1, phi 2, phi 3, so all with the transpose, phi 4 transpose, phi 5 transpose, like this way. So here I will get phi 1 transpose with k column, means something is there, that is a full column. Okay, then next one will be phi 1 transpose with k full second, like this way it will happen. Okay, this is full row but second column, and if I go here, it will be, let's say like I'm going for the fourth line, maybe third line, so phi 3 transpose 1, like this way this thing will come. Everybody agreed with me? No, you want to zoom it? Okay. Phi 1 transpose k colon comma 1 means full row first column. Okay, then if I see put that on k colon comma 2, that is full row but second column. Okay, so these are like a 1, 2, 3, like this way this will be split. And here if I just see 1, 2, 3, so like third if I put phi 3 transpose k colon comma 1, like this way this thing will come. Make sense? Now we are having again here phi, that is like a phi 1, phi 2, phi 3, phi 4, like this. Okay. Now, what I am trying, I just try to calculate only two terms. It will be okay. Now think, this full matrix with this give me what? It will be set in this point. So phi 1 transpose k colon comma 1 times phi 1 will be sitting at 1 comma 1. Then phi 1 transpose k colon comma 2 no, sorry, little bit mistake. Yeah. So if I just try to see the first term of that k11, means that full matrix, like the first term, if I try to see, means 1 comma 1, maybe I just say this is the k bar. So k bar 1 comma 1 is nothing but this is that phi 1 1 plus phi 1 transpose k colon comma 1 into phi 1 comma 2, like this way, because this will be multiplying na, like this way, means you are this term with this with this with this with this, like this way it will go. Make sense? So you will have this type of terms coming into picture. So that is your k1, and now I try to just calculate k12, that is the second term. Second term, if I try to calculating it, then means this full thing will this. So phi 1 dot transpose into k phi 21 plus phi 1 transpose k colon 1 phi 22 plus phi 1 transpose this will be 2, not 1. This will be 2. This will be 3. K2 3, like this way. Now, interestingly, you can notice that once you are try to have this way, that k11 into phi this, then this, then this, so that term will becoming 0. It will be reduced like this way. So I think you can do one thing. You will also check that, and next class we will start from here and we will try to do that full thing. Okay.